Hello, we are presenting a paper on optimizing large language models. LLMs demonstrate potential across natural language tasks. However, they struggle with problems that demand large analytical depth and longer-term planning horizons. To argue multi-step reasoning works like trees of thought and RAP with tree search algorithms. However, these methods rely on prompting a pre-trained model to serve as a value function. Consequently, they cannot benefit from in-domain training. They can also restrict it in scale, capped it as a maximum search depth of 10 or 7. To address this, the authors introduced TSLLM, an ALPHAZERO-like tree search framework. By leveraging a learned value function, TSLLM is scalable and handles search trees with a depth up to 64. Furthermore, it guides LLMs during both inference and training, iteratively improving the models. Next, my teammates will conduct a more in-depth discussion.
Thank you, Li Jiawei. For my part, I will present the challenges and motivation. Let's look at the challenges first. Existing framework like TOT and RAP face three limitations. First, unreliable evaluators. They promote the LLM itself to evaluate steps, causing several harmonizations. Second, shadow horizons. Search depths are capped at only 7 to 10 layers and failing in long horizon planning. Third is frozen model capacity. These interface-only methods cannot benefit from in-domain training, and means they are frozen model parameters instead of continuously upgrading the base LLM. Now, let's move on to the motivation behind TSLLM. To break these dead ends, TSLM introduced three breakthroughs. First is the learned value functions. We train an explained value function in network via DRL to provide robust guidance. And second is deep search scaling. As highlighted in yellow, we push the search horizon up to 64 layers deep and far exceeding TOT. Third is generalized place iteration. Tree search acts as a place improvement operator and creating a closed loop to the interactive training both networks. My part is over. Thank you for listening.
Hello, everyone. I will walk you through the problem formulation. The foundation of this framework is formulating the language generation process as a multi-step Markov decision process. The unique challenge here, as highlighted in the paper, is that both the action and state reside entirely within the language space. In this setup, the LLM serves as our policy, and the state at any given time step is simply the initial prompt combined with all previously generated tokens. Next, how do we define an action? The authors propose two distinct paradigms. First is sentence-level action nodes, treating each thought as an action. However, because enumerating all possible sentences is computationally infeasible, we are forced to set a maximum tree width to subsample nodes. To address this, the second paradigm is token-level action nodes, treating each individual token as a discrete action. While this eliminates the subsampling gap, it significantly increases the tree's depth, making the search algorithm much more challenging. Finally, the reward function. We operate in a highly sparse reward setting. As explicitly stated in the paper, any intermediate reward before the final step is exactly 0. The model only receives feedback at the very end of the generation. This extreme sparsity is the exact reason why we cannot rely on simple search and must introduce a learned value function, which other speakers will cover. Thank you.
Thanks, Xiaofeng. In this part, I will introduce how TSLM uses ALPHAZERO-like tree search for decoding and how it further improves the model. The key idea is that LLM generation is treated as a tree search process. Each node is a partial answer, and each action is a next token or reasoning step. The search follows 4 steps: select, expand, evaluate, and backup. A learned value function evaluates the leaf node, and the value is backup to early nodes. The paper introduces 2 variants. MCTS alpha starts from the current state, runs simulation, and chooses the next action by basic counts. After moving forward, it cannot trace back. MCTS rollout always starts from the roots and searches until complete answers are found or the computation limit is reached. So it uses more computation but may get better solutions. Finally, TSLLM also uses search results for training. Tree search finds better trajectories. Policy distillation trains the policy model on successful paths, and policy evaluation updates the value model. So the key point is search improves generation, and better generation further improves the model.
Now let's see how TSLM works. Let me walk you through where it was tested. The outlet will add TSLM across 5 tasks spanning 4 capability domains: mathematical reasoning and planning, logical reasoning, decision-making, and RLHF alignment. This breadth is that breadth. It proves the value function generalizes, not just on one task type. The 5 tasks are chosen to stress test different cognitive capability at different search depths. At one end, GSM-8K and Proton QA requires relatively shallow depths. At the other, Chess Endgame demands up to 34 steps, far beyond any prior method. Game 24 is a critical middle ground. Its combinatorial search space exposes exactly why a zero depth of 5 is used in TOT is simply not enough. The base model is LLMA 2 at 7B, tested from 125M to 7B. The key design choice: TSLM trains 2 separate networks, policy and value, where the value network learns directly from task rewards, not from promo-depth guesses. Such depth reaches 64 steps, against just 7 to 10 in prior work. TSLM is the only method with a learn value function. As a preview, on Game 24, TSLM reaches 34.8%, 3 times the best GPT 3.5 baseline. On GSM-8K, it achieves 52.5%, again outperforming all promote-based methods. I will now hand over to our next speaker for the full results.
Hi, here is AIT2309081 Lu Zhuoqing, and I'm responsible for experimental outcomes. In this work, the researchers proposed TSLLM, which is a special framework that can enhance the LLM's performance. First, in performance on different algorithms, ALPHAZERO-like search algorithms like MCTS-alpha and MCTS-rollout significantly outperforms the baselines in tasks with long horizon planning methods, and it shows the importance of value backpropagation, especially in deep search problems. And the learned value function can be more reliable than prompt-based GPT 3.5. You can see all the related results here. And then, when training TSLLM, it can further train LLM policy, value, and ORM, boosting the performance. However, in search aggregation, although the TSLLM does benefit from aggregation, but struggles to scale in small-scale problems. Finally, the application studies, which is used to verify component necessity, quantifying contributions, and enhancing transparency. The researchers first get a lot of data to train value function, and then they find that the search space and search width can significantly influence the performance. By expanding size and search width, the model's performance almost doubled from 43.8 to 80.7. Here are some related results detailedly proved in the appendix by the researchers, which are results of different nodes expansion on tasks and the results per task per aggregation. They all support the previous conclusion. That's all. Thank you.
Hi, I'm AIT2309080 Long Xiaoyu, and I'm going to make a short conclusion by talking about 3 parts: strengths, limitations, and future work. Let's talk about the strength of TSLLM first. The first strength is no longer relies heavily on external LLMs for evaluation. By learning its own value function, the framework becomes more stable and scalable. Second, it supports much deeper reasoning, with search depths of up to 64 steps, enabling stronger long horizon planning. Third, it creates a search training feedback loop, where high-quality search trajectories can be used to further improve the model. But at the same time, it also has some limitations. The biggest challenge is computational cost. Deep tree search requires extensive node expansion and value evaluation, making inference expensive. Another issue is the risk of reward hacking and evaluation bias. In addition, the framework is sensitive to hyperparameter settings, and for simpler tasks, the extra search cost may not always be worthwhile. So the future research can focus on improving search efficiency and reducing computational cost. Researchers can also develop more reliable value functions to improve evaluation accuracy. Another promising direction is hybrid search, combining sentence level and token level actions to balance efficiency and reasoning depth. Finally, adaptive search strategies could help determine when deep search is actually necessary, making the framework more practical for real-world applications. Thank you for your listening.